Hello, well, today we're going to have a look at serious sketching of tangent graphs. We've had a previous look at sine and cosine graphs, so here comes the third little player in the trigonometric graphs. It's tangent. Now, there's a few differences between tangent and sine and cos, which we'll explore in a moment. But first I want to have a look at our unit circle, and there it is. Now, okay, we know that tangent is the trigonometric ratio is the opposite over the adjacent, and there is the opposite, and there is the adjacent. Okay, now if we move anti-clockwise, that is the positive direction of any angle x, that's anti-clockwise, that means we rotate that little point E anti-clockwise around that circle where the centre of the circle is kind of like a hinge, you'll get that triangle we're looking at there, which has a much smaller blue horizontal adjacent side and a much bigger vertical opposite side. And you can see, as we're approaching 90 degrees, what's going to happen to that adjacent? Yes, that's right, it's going to vanish. So that's exactly why at 90 degrees tan is undefined, because you can't divide by 0. And this also applies to any progression from that point at that 90 degrees by 180 degrees and thereafter. So it applies to 270 degrees and any step backwards or forwards from 90 degrees by 180 degrees, because that's the points at which the adjacent side disappears and you just get a vertical line. You get it? So this graph is going to have asymptotes, because whenever you get to 90 degrees or its cousins, you're going to be in trouble. There it is. Now there's the graph. You see the asymptotes, can't you? There you can see one at pi on 2, 90 degrees, and you can see them. There's another one that's pi further on, or 180 degrees, and there's another one, another pi further on, or 180 degrees, and there's another one pi the other direction, in the negative direction of x. That's how it works. So it's pretty interesting, isn't it? It's so different from sine and cos. Now have a look at some observations from the graph. We can see that the graph repeats itself every pi unit. So the period of tan is not 2 pi like sine and cos, it's pi, just good old pi. Now I've just highlighted that to show you one period of the tan graph, and you can see that the span is only pi between asymptotes. Okay, what's the second point here? Oh yes, the range of tan is now all real numbers, because it goes from minus infinity up to plus infinity, so it's in fact R. Alright, now the third point, the vertical asymptotes occur. Now this is a pretty weird looking formula, so I wouldn't get too stressed about it, but it's sort of, I'm going to explain it to you. Basically the way I think about this is, the asymptotes are at pi on 2, 3 pi on 2, 5 pi on 2, and of course backwards the other way, so that would be minus pi on 2, minus 3 pi on 2, minus 5 pi on 2, etc. There we go. And if you think about that, with this formula, now it says there, there's a little k in there in that formula, and that k is any integer. So that an integer means plus or minus or 0. Whole numbers plus, minus, or 0. Now if you think about that, it's going to work. So take an example of k being 0, you'd get theta for the first asymptote would be just 1 times pi on 2. If you made k equal to 2, that would make that value of theta would be 2 times 2 plus, oh no, hang on, what, did I say k is 2? Yeah, k is, if it was 1, it would be 2 times 1 plus 1 is 3 pi on 2. If it was 2, it would be 5 pi on 2. So you can see it works like a charm. But I don't think it's necessary for you to think of the formula in that way, because it can be confusing to look at. Okay, now, what are we going to do now? We're going to get right into the heavy business of sketching this graph. First of all, I think we should highlight that we use the same procedure for sine and for cos, except we don't need the quarter cycle span for x, and we don't need the range or the amplitude in the y direction because the thing just goes off from minus infinity to plus infinity, so we don't need that. However, we do need the asymptotes. Yes, we do need those asymptotes. Okay, let's go. First thing, we'll get an overview of the transformations for this particular function which we're looking at, which is on the screen above us. Looks very complicated. Anyway, let's rewrite it in a way that's a little bit less threatening. Well, I think I can work out exactly what's happened here. So we'll do the old Dr. T, DRT on it, and we'll see what's happened. First, the D's. Aha, there's two of them. And one is a times 3 stretch in the y direction, or from the x-axis, and the other one is what's kind of like a compression, really. That's in the x direction, but we refer to it as a dilation of a factor of a half from the y-axis. Now, there's no reflections in this one. Phew, thank goodness. And we've got translations. Yes, we've got two of them. So what are they? Come on, you tell me. Yes, root 3 units up and pi on 6 units to the right. Very good. All right, now we're going to work out our working domain now. This is for me to work out what the x-intercepts are. Right, so we know that if x goes from those funny limits there which are specified in the question, I've worked my way up to the actual expression for what's behind the tan symbol, okay? And below me down, it's from 0 to 4 pi. Wow, that's pretty interesting, nice and neat, hey? So, that's our working domain. Now we're going to work out the new transformed starting point for this tan graph. And here it comes, there's the graph. So, at the new starting point, we normally start tan at the origin, so we'll say this expression behind the tan symbol would be 0, because that's what tan is normally, y equals tan x at the origin. So we're going to solve that for x now. Jolly good. So x is going to be pi on 6 at the starting point. So what's y going to be? Well, all we've got to do is plug in x is pi on 6 into our equation, and voila, we're going to get y. And I strongly suspect that first term there is going to be a great big 0. Of course it is. So there, we've got our starting point now. It's pi on 6 and root 3. That's great. Well, we're making great progress here. We've got a bit of an idea of what's going on. We've got the starting point, we've got the working domain. Now we're going to work out, oh dear, this is my least favourite part, but we're going to trudge on regardless, intrepid, and we'll find out the x-intercepts first, and we'll do the y-intercept second, because that's a really easy one. There's only one y-intercept. Ooh, did I say something wrong? Think about that. Well, here comes the x-intercepts. Yes, that's what that means when y is 0. So now have a look at that little number there, and I want you to tell me what angle that is. What angle in quadrant 1 that is, because we're going to find out over the page. Okay, here it comes. Right, our cast diagram. Now, which quadrants do we need? Well, our basic angle and our two negative quadrants for tan are now shown for you. Okay, the basic angle in quadrant 1 is pi on 6. Yes, I knew. Yes, you got it right, didn't you? Well done. So, that's the one we've got to work with to work out what all our equivalent angles are in quadrant 2 and 4, right throughout our working domain. Yeah, that's what I'm trying to say. Quadrants 2 and 4. Now, the working domain was, what was it again? Yes, it was 0 to 4 pi. So, hence, we can say that the whole expression behind the tan symbol is... Oh, what have I written there? Good gracious me. I'm saying it's 5 pi on 6 and 11 pi on 6. They're identifiable in the anti-clockwise direction from 0. The first one is a quadrant 2 angle, the second one is a quadrant 4 angle, and my little helper has arrived to help me today. He's saying to me, all you have to do now, from now on, is just cruise. That is, keep adding pi, because tan, unlike sine and cos, just repeats every pi. You don't have to worry about the whole thing of uneven kind of distributions of angles like as you do in sine and cos. These are always separated 180 degrees apart in tan. So let's go. Oh, look at that. Good heavens above. That's very easy, isn't it? Now, I think I've gone too far. But the good part about the working domain is it's very easy to spot that, because 4 pi is 24 pi on 6, so which one's out of range? Oh yes, I can see. Where is it? There it is. That one's out of range, so I don't want that one. Yeah, it's out of range, so I'll rub it off. Now I'm going to solve for x. It's easy now. Beautiful. Now, I probably need to see that on the left-hand side I've got pi on 6, and on the right-hand side I've got all these pi on 12. So look, rather than do my head in, I'm just going to simplify that line a little bit. Oh, no, I didn't. Oh, I take it back. I did it anyway. Sometimes I might write that as 2 pi on 12, just to help myself a bit, you know, that pi on 6 term. But I just trudged on regardless, and I got them. So they are, what are they again? Yes, they're my x-intercepts, aren't they? Pretty exciting. Now, remember I said the y-intercept occurs where x is 0, and there's only one y-intercept? I said something wrong. Do you know what I said wrong? Well, here it comes. Oh, my little helper's come to advise us. The working domain was from pi on 6. Oh no, that's not the working domain, that's the actual domain of x goes from pi on 6 to 13 pi on 6. So what does that mean in terms of y-intercept? Can you think about that? Doesn't cross the y-axis. Oh, they tricked us, didn't they? Good heavens. How nasty. No y-intercept at all in this case, because we've got a restricted domain which starts to the right of the y-axis in terms of x. That's a pretty interesting twist, isn't it? All right, now what's next on the agenda? Endpoints. Okay, we can handle that, no problem. We're just going to substitute x, the extreme left-hand and extreme right-hand value of x into the equation. So when x was pi on 6, we can work out that y is going to be root 3. So that gives us one endpoint, okay? Now one more to go. When x is 13 pi on 6, we plug that in, and oh, look at that 24 pi on 6 thing behind the tan symbol. Well, that's 4 pi, and tan of 4 pi, you think about that, because tan of 0 is 0, isn't it? And tan repeats every pi. So I think that that means tan of 4 pi is 0. Yes, it is. There you go. Isn't that interesting? So therefore, we've got our second endpoint. Wow. Oh, we're cooking along very nicely. So now, let's see what the next exciting thing to do is. Oh, the asymptotes. Right. Well, the working domain goes from 0 to 4 pi. We've got to keep that in mind. So, we're saying that the asymptotes for that funny expression behind the tan symbol would be at pi on 2, and just keep adding pi. It's just so easy with tan. So let's do that over the page, shall we? Ah, whoa, I forgot that. That one's out of range. That one's out of range. Of course it is. Yeah, so let's just get rid of that one. We don't want it. And we'll solve the asymptotes for x, okay? There they are. There they are. Oh, I rubbed that one off, didn't I? Now, here we go. Yep, and now I'm going to divide by 2. and then I'm going to add pi on 6. Now, look, I think I can smell a lowest common denominator happening here because that's getting really awkward. So what is the lowest common multiple of 6 and 4? Yes, it's 12. So why don't I just put the whole thing in terms of 12 so that I don't drive myself zotty trying to figure this out? That's easier, isn't it? Now I just got to add 2 pi on 12 to both sides, and oh, isn't it beautiful? There's my asymptotes. Gee whiz. Now we're finally on the home run now. We're going to sketch the graph, and we're going to use twelfths along the x-axis. And we have to label every jolly thing. Yes, we do. Now, over the page, and I will show you the graph. Here it comes. You ready? Da-da-da-da! There it is. Now, there's something wrong with this graph, and I want you to see what it is. The actual sketching of the graph is right, but there would be marks to lose on an exam if you did it like that, I would think. Depends on the way the question's worded, but usually you would lose marks. So what is wrong with this graph? Is my little helper there anywhere? Oh, I think I can see him running onto the screen. Oh, there he is. Okay, what are you going to say to us? Oh, it's labelling. What is wrong with the labelling? Have a good look. Have a good look. Alright, I think I'll put you out of your suspense. Label the asymptotes with their equations. Oh, of course. Let's do that. Now that looks better. Looks a bit like a junkyard, but still we labelled them, didn't we? Yes, we did. Now there's something else which is a pet fetish of mine. Even though the x-axis is, all the intercepts are labelled, usually they require them to be coordinate points. So please read the question and don't leave them as just intercepts if they ask for coordinate points. Now there's a third, more subtle thing in this particular case. Oh, jumping the gun there. Here comes the intercepts. And now, the third thing is, strictly speaking, for this particular graph, we should have a point of scale. That is a point marked on the graph to indicate the ×3 dilation in front of the tan symbol. Because there's no y-intercept, there's no kind of indication or verification on that graph anywhere to indicate what the stretching has been occurred, the 3 times stretching in the y direction that's occurred. So I don't think they'd ask you that in an exam, but look, that's strictly speaking what you should do, because it's not, there it is, yeah, there's the 3, and that's the 3 dilation. So that's got to be somehow shown on the graph, and a point of scale does that, because it's just not evident from the way that's been drawn, okay? Gee whiz, well it looks like we're finished, and it looks like a junkyard, but hey, it's a junkyard worth full marks. Oh, there's our smiley face. What have you got to say to us today, Smiley? Way to go. We nuked Tan, didn't we? Oh, look, he's singing a song. Oh, I think I'll sing a song too, and go away. So that was fun, wasn't it? Alright then, well, thanks so much everybody, and we'll see you next time.